Hi everyone, so today I have a really elegant question, and in this we're going to be talking about the roots of differentiable functions. So this is quite an interesting question actually, and this involves something called as the fundamental theorem of algebra, or like a result from the fundamental theorem of algebra. So yeah, let's see how that goes. So this is the problem B1 from the Putnam exam in 2015, and in this video we're going to be looking at roots of a function and its derivatives, and then we have functions that mimic the behavior of one another. We're going to see what that means. And after that, we have some book sessions for college mathematics, and at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so this is stating that let f be defined from reals to reals, be a 3 times differentiable function such that f has at least 5 distinct real roots. Right, 5 distinct real roots. That means they are real and they are distinct. They are not similar. Right, they are not repeated. So prove that this quantity, some summation of the differentiations of f, has at least 2 distinct real roots. Now here's the thing, I see a function f and I see and it's told that it has 5 distinct real roots and it can be differentiated thrice. So this f triple prime of x actually exists, so it's differentiable. We do not need to worry about the differentiability of that. So let me just maybe make like a table. So here let me compare the function and let me here write the number of distinct real roots that it has. So we have the function f of x, and they've said that it has at least 5 distinct real roots. Let me just write 5 at least. Yeah, how about f prime x? F prime x will have 4, right? F double prime x will have 3, and f triple prime x will have 2. And how does this come from? Well, it's quite trivial actually. It comes from something called the fundamental theorem of algebra, right? Fundamental theorem of algebra. And what does this mean? So it essentially states that if a particular polynomial has n roots, that implies its degree is n. Degree is n. So similarly, if its degree is n minus 1, what will be its number of roots? Its number of roots will be n minus 1. Right? Essentially, k roots correspond to a degree of k. And similarly, n minus roots will correspond to a degree of n minus 1. Now, a function f, so let's consider the function f has degree n. Right? So assuming that the function has degree n, what will be the degree of its derivative? It'll obviously have degree n minus 1. Right? Because if you remember the derivative, the formula for that, the derivative of x raised to power n is n times x raised to power n minus 1. So you see the degree, or like the power of x, the power of the highest term, actually decreasing by 1, right? So if f has a degree n, then f prime will have a degree n minus 1. So similarly, that's what I've done over here. F has a degree 5 real roots, so degree 5 at least. Then f prime of x has to have 4 at least. F double prime x has to have 3 at least, and f triple prime x has to be 2 at least. So okay, I hope that's pretty clear. Great. So now that we have maybe kind of thought about this a little bit, that f triple prime x will have at least 2 distinct real roots. And going back to what we need to prove, we need to prove that this composition in a way, or this summation of f plus 6 f prime plus 12 f double prime plus 8 f triple prime has at least 2 distinct real roots. So what do we really need to do over here? So we need to think of a new function. Maybe let's call it a g, right? The new function g of x, and the third derivative looks something that was given to us in the question. So when I maybe find the third derivative of g of x, it should be similar to something like this, right? It should maybe look like f plus 6f prime plus 12f double prime plus 8f triple prime. Hey, this is what was given to us in the question. So it looks something similar to that, right? And what else it needs to have? Its roots. So the roots of g should mimic the roots of f. Because we do not want to dive into should g be differentiable, is g differentiable, is it not differentiable? No, in the question they've given us that f is differentiable, so we need to pick a function g that is differentiable, right? So should be differentiable. So how can we pick a function that is differentiable and its third derivative is something like this? Well, all you really need to do is you need to pick a function which mimics the roots of f and whose third derivative is of this form. Therefore, essentially the roots of g should mimic the roots of f. And the easiest way to do that is choose an exponential function. So what I'm going to do is I'm going to define g of x as e raised to power ax times f of x. Why did I do this? Because you see, we need something of the form f triple prime x and a lot of the other things. So maybe once I find the third derivative of g, I'll get the third derivative of f on the right hand side as well, using those product rule and all of that. So there will be some term of, third derivative of f somewhere in the right hand side. Right, so that makes sense. That is point number one. And the point number two is that the roots of the g should mimic the roots of f. Now you see an exponential function. E raised to power ax equal to 0 has no real roots. Right, because for no real value of x will e raised to power ax ever be 0. So therefore, if f of x has, let's say, n roots, so this also has to have n roots, because this other thing is not contributing anything. It's just adding some, it's just being multiplied to f of x, but essentially in terms of roots, it's not producing any extra roots other than what we already have for f, right? So that's great. So now once that we have this function g, or once you define this function g, all we really need to do is differentiate this, right? Now just for like a little bit better understanding, so g will have 5 real roots, right? At least 5 real roots, because like I said before, this e raised to power ax is not contributing anything, and we know that f of x has 5 roots, so g of x also will have 5 roots, right? So g will have 5 real roots, g prime will have 4 distinct real roots, at least distinct real roots was given the question, at least distinct real roots, yeah. G double prime of x will have 3, and the third derivative of g will have 2 distinct real roots. And yeah, this is obviously at least. All of these conditions are given us in the question. Okay, great. So maybe let's just proceed with differentiating this, right? So g of x was a times e raised to power ax, e raised to power ax and f of x, right? And let's just differentiate this. So we use the product rule. So you will get a times e raised to power ax times f of x, right? Plus e raised to power ax times f prime x. Okay, great. Now you again find the second derivative. So differentiate this again. Again, you just use the product rule for all of these things. You will get something that looks like this, plus 2a e raised to power ax times f prime x plus e raised to power ax times f double prime x. So if you kind of maybe see the pattern, you have g double prime x on the left hand side, f double prime x on the right hand side. Now once you differentiate again, you'll get f triple prime of x. And that's something similar to what we need in the question as well. So the third derivative of g would look like this. E raised to power ax, I can take that common. And then you'd get a cube f of x, okay, plus 3a squared f prime x plus 3a f double prime x plus f triple prime x. Okay, great. Now what do we need next? So we have this f triple prime x on the right hand side, right? And this is what I was referring to before. There is going to be some term of the third derivative of f on the right hand side. Now what do we need in the question? We need something of the form f plus 6f prime plus 12f double prime plus 8f triple prime, right? This is what we need. We need to prove that this will have at least 2 distinct real roots. Okay, great. So you see we have this f triple prime on the right hand side, but we need 8 over here. So maybe let's just multiply both sides by 8. And once I multiply both sides by 8, I'll get something like this. 8g triple prime x equal to e raised to power ax, 8a cube f of x plus 24a square f prime x plus 24a f double prime x plus 8f triple prime x. And what's this a? A is just a constant, right? A is something that we have come up with that ourselves, right? A was not given in the question, so we can really adjust the value of a depending upon what we want, right? Because the a has been introduced by us, right? In fact, G also has been introduced by us. So what I'm going to do is I'm just going to set A is equal to 1 by 2. And once I do that, the right hand side will look very, very, very similar. So once I set A is equal to 1 by 2, 8G triple prime X will be nothing but E is for X by 2 times F of X plus 6 times F prime X, 6 times F prime X plus 12F double prime X plus 8F triple prime X. What does that mean? So 8G, the third derivative of this is E raised for X by 2 times F plus F prime plus 12F double prime plus 8F triple prime. And that is what we need to do. So this is the purpose of choosing this G, right? When you differentiate it thrice, you should get something of the form that was given to us in the question. Right? This long form that we see on the right hand side. Now, going back to up top, so we have seen that the third derivative of G has at least 2 distinct real roots, right? So it has at least 2 distinct real roots. So this quantity will have 2 distinct real roots. This will have 0, obviously. So this also has to have 2 distinct real roots. So therefore, we have indeed proved that F plus F prime, 6F prime, plus 12F double prime, plus 8F triple prime has at least 2 distinct real roots. And that concludes the problem. So yeah, it was quite interesting actually. And the key to it was essentially coming up with this function G. And if you see that an exponential function can work beautifully over here, that's it. Your problem is done. Another reason that I found to take the exponential function was because it's easy to differentiate. You know, you can experiment some other functions, but the problem with them is that they might not be easy to differentiate. So you really can come up with a function which has no real roots, but then it also needs to be easy to differentiate so that, you know, your work can be cut out. So yeah, the exponential function fit us perfectly, and that sums up this problem. Okay, so moving on, we have certain book sessions of college mathematics, Introduction to Real Analysis, Principles of Mathematical Analysis by Rudin, Calculus Volume 1 and Volume 2 by Apostle, Topology, Contemporary Abstract Algebra by Galian, Topics in Algebra by Herstein, Abstract Algebra by Dermot and Foote, Linear Algebra done right by Axler. Okay, so at the end of a similar but challenging problem, and it states that let f of x be a differentiable function in 0 to 1, and they've given us some initial condition, right? f0, f1 is given, 0 and 1 respectively, and it is also differentiable in 0 to 1. So this looks something similar to a theorem that I may have seen before, right? So prove that there exists real numbers x1, x2, x3 all the way up to x20, 21 such that they are somewhere between 0 and 1 and are increasing, and this summation is equal to 20, 21. So we need to prove the existence of certain xi's, of these xi's. So we'll try it out, and if you're able to solve them, let me know in the comment section below. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.